Good day, class. So I decided to have a recording ahead of the last two topics for differential equations, and that is the variation of parameters and the operator methods in handling higher order linear with constant coefficient differential equations that are said to be non-homogeneous. Now, our last topic, which is Laplace transformation, will be discussed on a next set of slides. But this one, I decided not to have a slide because of the nature of the solution, which really entails that I will have it written so that you can follow through the procedure in going about the use of the method. So as a start, we're going to use the method of variation. So I have really a problem with my pen. Variation of parameters. So we use this for higher order linear non-homogeneous differential equations. So variation of parameters. So I will discuss as I go along the procedure on what's the difference of this one with the method of undetermined coefficient that we have previously discussed. So let's say, for example, you're given a differential equation which is second order. So it's y double prime minus 3y prime plus 2y being equal to x e raised to x plus 2x. So this can be solved actually using the method of undetermined coefficients by considering this as a product of two functions and this one as a first degree polynomial. So you will have two particular solutions in this case. One totally dealing with a non-homogeneous higher order differential equation with only this written on the right side, and another one which will only have this written on the right side. So what you do, you just take the sum of the two particular solutions and add it to the complementary equation or complementary solution based on what is written here on the left side, specifically basing it on the roots of the characteristic equation made from the derivatives of the unknown function and the unknown function itself written here on the left side of the DE. Now in here, we will not use the separation of, shall I say, the two parts of the solution using method of undetermined coefficient, but primarily our solution will be based on the form, specifically on the form of the complementary solution. So if I will write the characteristic equation for this, that would be m squared minus 3m plus 2. Now, this is our characteristic equation, and upon a factoring, of course, when you do factoring, you have m minus 2 and m minus 1 being equal to 0, telling you that you have real unique roots in the form of 1 and 2. So with these roots 1 and 2, we can right away write the form of its complementary equation. So if we will write the complementary equation, or that is, sorry for this class, or that is the complementary solution, you will have it as yc equal to, so we would write it as e raised to negative x, or rather positive x, and c to e raised to 2x. Okay, so this is our complementary solution. Now, in the method of undetermined coefficient, what we do is have this and then determine the yp and add the 2. That would be our complete solution using the method of undetermined coefficient. What we do with variation of parameters is from the form of the complementary solution, we write the particular solution. And this time, we don't consider c sub 1 as arbitrary constants, but rather we consider these two as functions of x. So that we won't easily get confused on what is c sub 1 and c sub 2 here, I would represent the two arbitrary constant here as a of x e raised to x plus b of x e raised to 2x. So what we have done is, based on this form of the complementary solution, now in variation of parameters, we have written the constants as functions of x, or functions of the independent variable x. So this would mean that if we're going to get the derivatives later on of this form of our particular solution, we will be dealing with the derivative of a product of a of x times e raised to x plus b of x times e raised to 2x. Now, how it's going to be? So it's something like this. So if we get the first derivative, I will not anymore write the p. I will just base it. After, by the way, we're done with writing the form of our particular solution using this method, you totally forget this. It's like it's not there anymore. Okay, now we will be concentrating on this form of our y. And so, as I will not need to write down the subscripts, just know that I am now getting derivatives of this form of the particular solution. So if I get the derivative of the above equation, that would be a prime e raised to x plus e raised to x. For the second part, we'll have b prime e raised to 2x plus 2b e raised to 2x. So what I'm doing here is I'm using product rule. Now I have the second term multiplied to the derivative of the first. So generally I will just write the derivative of a of x as a prime because I don't know specifically what is a of x. Then I will have the derivative. I will have the first term multiplied to the derivative of the second. Now, in here, we do the same derivative of the product. So, second terms times the derivative of the first, so that would be b prime e raised to 2x plus the first term times the derivative of the second, which is 2e raised to 2x. Before we go to the next derivation, in this case, since we want something very simple, we will have to, shall we say, we will not anymore consider these two terms having the derivatives. When you do variation of parameters, and if you're going to read from other reference books, actually this particular method is referred to as the reduction of order. We reduce the order of our given higher order differential equation by differentiating the form that we have written for its particular solution, but subsequent derivation entails that we neglect the terms that have the presence of the derivative. What do I mean? Since our original DE has the second derivative, you can see this one. So far we have only done the first derivation. In the method of undetermined coefficient, these terms that have the derivatives, this one, we don't include in the next derivation. So meaning, I will only differentiate this and this again. That will be reflected on my second derivative for my y. So if I will do that, the y double prime will simply be differentiating the remaining two terms here, because these two terms that have the derivative will be taken out of the picture. So you'll have, in this case, the same thing, a e raised to x plus a prime e raised to x plus, so you have 4 b e raised to 2x, that would be this differentiated multiplied to this, plus 2b prime e raised to 2x. So the derivative of this, so the derivative of this one will be this 2. Now, the derivative of this one will be this 2. Now, what we'll do next will be the same as what we have done with the method of undetermined coefficients. We will substitute the derivatives of our unknown function to the original differential equation. So, this is our original differential equation. So, we will do that. That would then be for the y double prime, we will have a e raised to x plus 4b e raised to 2x plus a prime e raised to x plus 2b prime e raised to 2x, and this will be equated to what we have there on the right side of the DE. And by the way, class, this is just the second derivative. I will not for now write first the right side of the DE. Now, what we do is we write the first derivative, but our first derivative in the original DE is being multiplied to -3. So, we will do that, and we will write it in columnar way. What do I mean by that? So, I will write here the first derivative, this one, this first derivative here, I will write it, but first I need to multiply it by 3 because as you could see here, it's being multiplied to 3. Actually, -3 specifically. But I will only multiply those terms that I have not crossed out. So, meaning my y prime will only be a e raised to x and 2b e raised to 2x multiplied to -3. So, if I will write it under the term which is similar to form to the first term, which is the y double prime, it would be something like this. So, I will have negative, so yeah, sorry, 3ae raised to x, and I will have negative 6be raised to 2x. This is after I have multiplied the y prime by -3. Then the last term that you see here in the original DE is twice of the form of the particular solution, which means that I will need to multiply this by 2 and add it in column way to this first two terms in my DE. So I will have to write here 2ae raised to x, and you will have plus 2b e raised to 2x. Then I will add. So the process here is addition. If you notice, if I will do addition, class, all the terms that doesn't contain the derivatives of the coefficients will be gone. So what is left is just a prime e raised to x plus 2b prime e raised to 2x, which I need to equate to x e raised to x plus 2x. So this is now the result of my addition of the derivatives, the two derivatives of my unknown function specifically, and the unknown function itself to the original DE. Now, what will I do next? So this is, let's say, our equation 1. Okay, this is our equation 1. So if you recall, I'd like to go back here. These two were taken out of the picture because, so I'd like to write it in red, because we have a prime e raised to x plus b prime e raised to 2x being equal to 0. So the purpose these two were taken out because the sum of these two was set to 0. That's what we do always when we do differentiation. in the previous derivative, we set to 0 the sum of the terms which have the derivatives of the coefficients. So in that case, the coefficients here that I'm referring to are the a and the b. So whenever you have these terms which has derivatives of these coefficients, you will get the sum of those terms and set it equal to 0. From this one, we can have a relationship which is a prime e raised to x being equal to negative b prime e raised to 2x. So we can set this as our equation 2. That way, I can work this equation with the equation 1 that we have here to simplify the form. So you can see here that your a prime e raised to x is negative b prime e raised to 2x. So you have here a prime. So if we will now deal with equations 1 and 2, that would be then this a prime I will replace by negative b prime e raised to 2x. Plus, you have here 2b prime e raised to 2x, and everything on the right side will be copied. Okay, so you have that. Now, this will yield, if you are going to do the addition, then this will yield a b prime e raised to 2x being equal to x e raised to x, plus 2x. Now, we will continue here. We will isolate the b prime here. So, I will divide the entire equation by e raised to 2x. So, the left side will be left with b prime. And what you will have for the first term here is e raised to, or x e raised to negative x. Why is that? Because you will divide this entire right side, same thing here, with e raised to 2x. So that would mean that what you will have here is e raised to negative x, and the second term will be plus 2x e raised to negative 2x. Okay? So you have it here already. Now, how do you find the b, or the b of x specifically? That will entail that you integrate this side and this side of your equation. If you do integral for this, the b prime will be b, or specifically the b of x now. And this one will, of course, use the integration by parts. So for the first part, you will have a u1 equal to x, a du which will be equal to dx, your dv which will be equal to e raised to negative x, and a v which would be equal to negative e raised to negative x. Now this term, I would like to circle it. This term now will be like this one, processed like that. So if we will write its solution here, you will have uv minus v du. So you have uv, so negative x e raised to negative x minus v du. But since this is minus, so this would be plus integral of e raised to negative x dx. Now, for the second term here, this is your second term. It's another integration by parts. So you will have here u being equal to x, your du will be equal to dx, your dv will be equal to e raised to minus 2x, and your v will be equal to, if you integrate negative, negative 1/2 e raised to negative 2x, because you need to introduce the negative 2 in the integral here. That way you can have eu du. So negative 1/2. Then you will write the equivalent integral here. So plus, but don't forget, class, that since I did not include the 2, all your products here will be multiplied by 2. So your uv will be multiplied by 2, so that would be then negative. So this would be now negative xe raised to negative 2x. And we have minus the integral of v du. But since if you notice minus the integral, this is minus, so that would be plus. So plus, okay? However, you have the 2, so you will have plus the integral of v du. So e raised to negative 2x v du dx. Okay, so uv times 2, so that would be negative x e raised to negative 2x minus minus, so that would be plus this one times 2 also v du, so e raised to negative 2x dx. So this is now the processing of the second term. So if we will simplify our b of x, okay, this would be, so I'll write here our b of x. B of x then is equal to, so this we copy and this we copy. You have something common between the two, and that is x e raised to negative x negative. So I will place here negative x e raised to negative x, and I will multiply it by 1 for this. And this one, you need another, you have e raised to negative x to make it negative x e raised to negative 2x for this one. If this you will integrate, that would be minus e raised to negative x, the integral of this, and this if integrated will give, sorry for this guys. If you will integrate this, that would be negative 1/2 e raised to negative 2x. Now I'd like to simplify this. So you have here e raised to negative x and negative x as being common. I would like to copy this on the other side. So your b of x will be now negative x e raised to negative x. This would be 1 plus e raised to negative x. So that would be, this is for our first two terms. And for the next terms that we have, you have common is negative e raised to minus x. So I will factor that out. So minus e raised to negative x. And what you'll have here is 1, because this one is negative, and this one would be plus 1/2 e raised to minus x. So plus 1/2 e raised to minus x. Now you could see that this is already your b of x. What is that b of x that I'm referring to? That b of x is this b of x here, that you will write as your solution part, or the second term coefficient of the solution using the variation of parameters method. So we still do not know the a of x. So we can actually get an expression of a of x here on the same equation that we have set to 0, but this time you will let b prime of e raised to 2x equal to negative a prime e raised to x. So we will just place the negative here, and we will replace the b prime e raised to 2x in this equation here in this equation, we will replace it by negative a prime e raised to x and then do the procedure that we have done here. So we will do that. But for now, we already got the b of x. So next will be the a of x. So from equation 1, so this is your equation 1. I will substitute negative a prime e raised to x for b prime e raised to 2x from here. So b prime e raised to 2x is negative a prime e raised to x. So I will do that in here on this equation. So I will copy the a prime e raised to x. So from 1, so you have a prime e raised to x, and your b prime will be down negative 2 a prime e raised to x. The b prime e raised to 2x is replaced by negative a prime e raised to x. So I just affix the 2 here. The right side would still be the same because our right side is not affected on what we are doing on the left side. It's only affected when we do the integration already. So in here we could see that it's negative a prime e raised to x being equal to x e raised to x plus 2x. Now, if we will divide the entire equation by e raised to x, we will, our negative specifically, we will be isolating the a prime on the left side, and we will have here on the right side negative x. It cancels the e raised to x on the first term minus 2x e raised to x in here on the second term minus 2x e raised to x. And then for us to be able to know the a, we need to integrate, of course, the equation that will yield the a of x just like the way it yielded the b prime of x here. So I'd like to have that underlined because we'll add that later with the other one, and we will now process the integral of what we have here on the left side. So we have a, so this is now a being equal to d. Now I'd like to copy what we have there, the integral of negative x dx. So the integral of negative x dx will be negative x squared over 2. Okay? This one, negative x dx is negative x squared over 2. This one will be another by parts. Sorry. But by the way, this should be negative. Another by part similar to what we have here for x e raised to negative x. So you see this? So it will be actually yielding the same integral here. Only that since we have, in this case, it's also negative. So I will be copying this one. This one is the integral of x e raised to negative x. Whereas this one is negative x e raised to negative x. We will just simply multiply it by negative 2 later. So what I'll do, I'll copy these two here, or specifically I will copy this one and have this process by integration. So I will have minus 2 because that's my multiplier. Then I will multiply it by e raised to negative x minus e raised to negative x. Let's see if that will be our processing. So for this integral, positive, this will be your answer. Negative x e raised to minus x, and if this is integrated, that would be negative e raised to negative x, and that's what I've done here. Okay, negative, and this one will be negative. So I think I missed on the sign, so this would be negative. Now you may wonder where is this negative 2 coming from? Remember that our original integral is negative 2. So I just copied the integral of x e raised to negative x on the other slide here, on this sheet here. That way I will only need to multiply it by negative 2. Okay, so this one already processes this part of our integral for our a prime of x. So we can have right away the answer here. So I will have here negative x squared over 2. These two have negative e raised to negative x as common. So I will have here plus 2 e raised to negative x. I have already negative, so that would be positive 2 e raised to negative x. And I will have x plus 1. Because I took out negative e raised to minus x here. So then that would be only plus 1. And this one, that would be 2x e raised to negative x. So this is already specifically your a of x. Now, what about the solution of our differential equation in this? Okay, so this is your a of x. I like to underline it in red. And you have here your b of x. Now, since by the way, we have integrated here, and this is an indefinite integral, no limit, so we need to write the constant of integration here. You can have it as letter a or letter b, or you can have it as, in this case, since this is b, we will have this as c sub 2. And in here, same thing with the way we integrated the a prime to make it an a. So I will introduce here the constant of integration c sub 1. So if you will substitute this a of x and this b of x here in the original form that we have, this is our yp, or this is our solution already using variation of parameters. You will be now having the solution of the DE using variation of parameters. So your a of x has to be multiplied to e raised to x. So remember this. It needs to be multiplied to e raised to x. And for our b of x, it needs to be multiplied to e raised to 2x. So what we'll do then, we will multiply the 2 by that. Then we will have now the solution of our DE. So I'd like to start with a of x because it's the first term that I have. So therefore, your y, the solution of your DE, will be equal to all this should be multiplied to, again, e raised to x. So I will have c1 e raised to x minus x squared over 2 e raised to x plus, if this is multiplied to e raised to x, the e raised to minus x will be gone. So 2 times x plus 1. So this is your a of x multiplied to e raised to x. Now we go to your b of x. So your b of x is this entire expression that we have here. And it needs to be multiplied to e raised to 2x. So we will multiply all of this by e raised to 2x. So I will have here, so we'll have plus, I'll write it here below because that this will be too lengthy, c sub 2 e raised to 2x for my arbitrary constant. Then, I'd like to go back here. The first here, I will multiply to e raised to 2x. So, initia madula. This will be gone, leaving us negative x e raised to x. Positive already. So, negative x e raised to x. because I have multiplied this term by e raised to 2x. So it will now be positive e raised to x. I just copied the negative x here. Then this will be multiplied as well. So you will have 1 plus e raised to negative x. Okay? For the second term, you do the same. You will multiply this one by e raised to 2x. So then that would be e raised to x. So negative e raised to x times 1 plus 1 half. Okay? 1 plus 1 half, you see this, e raised to minus x. E raised to minus x. Okay. Now, you can rewrite this in such a way that all the terms that have the C1 and the C2 will be written first, followed by the term which has the highest degree. So, this would be followed by this one, by this, and this one. But nonetheless, class, this is already, the equation that you are seeing here is already the solution to our non-homogeneous second order differential equation using variation of parameters. Actually, this procedure is lengthy and it will require integration, and most of the time the integration is integration by parts. So you need to practice using this particular method in other non-homogeneous higher order differential equations, so that you will be familiar on the procedure and how you go about the procedure. But nonetheless, class, we will just be repeating the set procedures that I have done here in other higher order differential equations. So what is important is you know the steps on how you're going to go about it. So to summarize, I'd like to go back to the steps that you will do. If you're given a non-homogeneous higher order differential equation, non-homogeneous in the sense that your g of x here is not equal to 0, the first part of the process is writing the characteristic equation. And the goal is for you to determine the roots of that particular characteristic equation. So write the characteristic equation, determine the roots of that characteristic equation, and write its form. So this is the form of your complementary solution. From the form of your complementary solution or complementary equation, you write the form of the solution, the complete solution of your given non-homogeneous higher order differential equation. This time, replacing the arbitrary constants c sub 1 and c sub 2 by functions of x, or expressions which are functions of x. And then once you have done that, you forget about the complementary equation that you have used as a basis, because you will now differentiate your form of the complete solution for your higher order non-homogeneous differential equation. So differentiating would entail that you use the product rule of differentiation. So you do that for the first differentiation. Since you have until second derivative in our example, before you go to the next differentiation, make sure that the sum of all the terms that contains the derivative of coefficients of your independent variable should be set to 0. So we set to 0 the sum of the terms that has derivatives of your coefficients. And then you do the next differentiation. So what you need to differentiate, by the way, is just the two terms here, and this would be your resulting derivative. Now, if you will have to follow the method of undetermined coefficient after you have done the differentiation, you go back to your original DE and substitute the derivatives. So we have done it here. This is for the second derivative. This is for the first, in which the derivatives of your coefficients, the sum of which were set to 0, and this is for your form of your complete solution. It was multiplied by 2. This one was multiplied by -3. When you take the sum, you will notice that all the terms that does not have the presence of the derivative of the coefficients which are in terms of your independent variable will be gone. That's one way of checking that you're doing everything right, when nothing will remain of the terms that does not have the derivative of your coefficients. Then you affix the functions written, or that's your g of x written on the right side of your dE. Now, since you have here an equation which has two unknowns, the a prime and the b prime, you get a relationship between these two based on the sum of the derivatives of these coefficients set to 0 before you did the second differentiation. So you get a relationship from this equation. So this is it that we have taken. Then you substitute it in here so that you will have only one remaining unknown. The goal is you will determine the b of x in this case. So b prime, it's still b prime. You need to isolate it here, so you need to divide the entire equation by e raised to 2x. After that, you need to integrate because you want the b of x. When you did the integration, this is already your b of x, and we just affix the arbitrary constant c because we are actually dealing with an indefinite integral here. You do the same when you want the a of x. So when you want the a of x, you need to express from equation 1 the b prime of 2x in terms of a prime e raised to x. And again, integrate to give you the a of x. So this is your a of x with the arbitrary constant. The last part of the solution would entail that your a of x and your b of x that you got after integration should be multiplied to whatever function it is to be multiplied to based on the form that you have written. So your a of x should be multiplied to e raised to x, and your b of x should be multiplied to e raised to 2x. So what happens now is you have this particular solution for your non-homogeneous dE. Of course, it pays to rearrange because it's easier to understand if the terms that have the arbitrary constants are written here and the rest are already not containing the arbitrary constant. The term that has the arbitrary constant actually in the method of undetermined coefficients is your complementary solution or complementary equation. The rest of the terms that does not have the c is your particular solution. So this is, class, the method of variation of parameters used in determining solutions of higher order differential equations which are said to be non-homogeneous.